Right, welcome back to the industry track. We're going to kick off this block of presentations with Cora Liebig, the CEO of Chromatic 3D, talking about industrial elastomers for AM. Just as a reminder, if you have questions for any of our speakers or panelists, there is the Q&A tab up at the top. It's separate from the chat, so go ahead and put your questions in there, and feel free to upvote those questions that you want to see answered, and we'll try to save time for that at the end. So Cora, I am going to invite you to come up on stage. You should be able to turn on your camera and mic, and we'll get started.
Great. Oh, I need to share again. Here we go. Give me a moment here. Here we go. Well, thank you very much, Stephanie, for the introduction and also the invitation to speak. I really appreciate it. What I'm going to tell you about today is our efforts at Chromatic 3D Materials to develop really industrial grade elastomers for 3D printing. Our technology we call REXAM. It's reactive additive manufacturing. And really what we're able to do with our technology is print with cross-linking materials. And really for the sake of this discussion, we're going to call thermoset anything where it has to undergo mixing for a reaction and to form the materials. This is in contrast with a thermoplastic where the act of forming a material comes from melting. So I'll tell you a little bit about our company and what we've been able to demonstrate. So my background, I've been spending a career in materials development, product development in both startups as well as large corporates. So I spent about 12 years at Dow Chemical and then at Segetis, a startup doing clean tech. And I've been fortunate in that this has really exposed me to industrial manufacturing and use of plastics and additives really throughout the world and in a variety of processes. My background is in chemical engineering, and I have more than 25 patents. So let me tell you a little bit about thermoset 3D printing. So the reason why I started Chromatic back in 2016 was that we wanted to develop a technology that would allow you to print materials that are in common use and are like I like to call them at the top of the material pyramid in plastics. So what that means is that they are some of the strongest materials because you have to undo a cross-linking reaction in order for it to fail. And this means that you end up getting high strength, high heat performance, and really very durable products. And really for 3D printing to really move into industrial areas, we need the materials that we use in our printing processes to be very high strength and frankly, just like the materials they've been using, and offer the same versatility that materials that are in common use in industry offer. So you touch elastomeric thermosets all the time. So these, you find them in seals and gaskets. They're in medical devices. They're in vehicles. Your footwear, if you have a really good pair of hiking boots, the sole of your hiking boot is probably a thermoset polyurethane. And it goes into your apparel as well. And so like I said at the beginning, a thermoset is something that reacts to form instead of melts to form. And they're really critical for a lot of durable goods across multiple industries. And they're also so what Chromatic does is we make industrial materials printable. So we develop the materials, we develop the printers, and we develop software to enable printing with those materials. And the process we use like a modified FDM process. Instead of melting, we take two materials and take them through a mix head and that mixing action starts the polymerization. So it's not activated by light, it's just activated by a simple mixing of two materials. At Chromatic, we synthesize our own materials. We have a lot of formulation expertise. And the other important element here is that the printing methods are quite fast, and we're able to build the printers from relatively low cost systems. The printing itself is conducted at room temperature, so very easy to have an open printing environment. And here's an example of the printing process. Here we're demonstrating what we call smooth mode printing, where the bead size is much bigger than the actual resolution size and smoothness of the print. We're able to build very high overhangs. We can do wall thicknesses that are anywhere between, half a millimeter and larger, so we can do very thick parts. And we are able to achieve overhangs without supports really well, even horizontal, and more easily 15 degrees. So this is a very versatile and technique. And what makes it versatile is the fact that we're able to blend a lot into the formulas. So we're able to incorporate additives, etc. And what's going on here during the print, when they start to come into contact in that mix head, they're starting to but then down, the material coming out is partially reacted, but then it really reacts very well with all the materials, with the material below and the substrate. So the result is that you get a part with isotropic properties, and that's really important. We don't see any print. Some of the things that we're able to extend this to is that we're also able to print on top of other things. And part of what we've developed in line with that is scanning software for doing non-planar printing. So we can scan, in this case, SOC, and then import that surface. We can take a flat shape or print and then directly print it on of that surface. And the other important feature here is the fact that the materials are reacting as it goes, means we have really strong adhesion to the layer below. So in this case, we're able to really have very strong adhesion to the SOC. And repeatedly, when we print on textiles, we've been able to prove that we have adhesion that's as strong as the textile itself. So the parts, if you try to peel them off, really do not peel off. And this is one of the features of having a reactive system rather than a melting system. And we can do this on textiles, metals, and other plastics. Now, a lot of people in 3D printing, because elastomers haven't necessarily been a strong suit for the 3D printing material palette, a lot of people in 3D printing don't recognize that there's a really large market out there for solving this problem. So as we've calculated it, it's about a $4 billion opportunity just for elastomers. Now we envision extending beyond elastomers, but in our technology, but where we're seeing the opportunity is in industrial parts, seals and gaskets, tooling, material handling. These go into virtually every piece of industrial equipment. We see a lot of opportunity in apparel and textiles because we're able to add and print features, very durable features on top of apparel and textiles. A lot of applications in transportation, also for printing on textiles, but also for printing in a lot of interior parts that need a soft touch. And in medical, there are also a very large range of applications. Elastomers are used for in-body as well as external applications for medical because it can conform, it bends to force, so anything that you associate with soft touch usually comes from an elastomer. And then there's also a lot of applications in aerospace and defense, in not only in maintenance, but also rocket designs and drone design. So some important features of what we're able to achieve at the elastomers that bring it to full industrial strength. First off is that we have dense solid parts. Where we lay down material, there are no voids. And so what you see on the left here is a CT scan of a part, and the CT scan will reveal any gaps or voids. There's really none in our printed parts. If you take an analogous part from FDM, you often have a lot of voids. And the important thing about these voids is that you can print a part with a material that has good base properties, but in the part itself, the voids can actually lead to failures and can cause a part to fail prematurely relative to the failure point of the material. And so the fact that we're able to make dense, solid parts is really helping us penetrate these industrial markets and move into industrial markets for 3D printing. And I've mentioned printing on textiles, just some other examples. We're able to print directly on a metal piece. I'm going to show another example of this part in particular. We're able to eliminate seams in textiles by printing a bead instead. And we're able to incorporate sensors during the print. And so what we find when we work with our customers is that the fact that we can print on top of other things really allows the customers to eliminate a large number of assembly steps and really bring that full value proposition of 3D printing to the fore and to the manufacturing floor. So just a couple of use cases here. In this case, and this is something, if you follow us on LinkedIn, you would have seen this story, and I know that Stephanie also covered it. This is a trackpad where an antique tractor restorer wanted to replace track pads on a John Deere. So this is a metal base that then we printed a shell, and then we have formulas that kind of match a cast urethane with the shell urethane, and we're able to print completely a part here onto the metal, and it had an embedded screw. And here's an example of just riding on these printed parts in the state fair. This tractor's been running now for well over a year with printed track pads, and the wear and tear is just as good as anything they'd expect from the original parts. I see a question about the embedded sensors. We've been looking at embedded sensors mostly for grippers and end effectors on robotics, but this is something where I think there's a lot of potential applications, including bringing in IoT for failure and things like that. So that's just answering that question I see on the Q&A. But anyway, is that these printed pads on the metal piece, that adhesion is just very strong. This where we're taking additive manufacturing into applications that many people would not consider to be possible. And the reason why we're able to do it is because we're able to bring these industrial grade parts and print it in a way that we're able to maintain that isotropic. And we were really excited when Daimler came to us. Our materials had passed their qualification standards quite some time ago, and they came to us because they were having a supply chain crisis for their bus lines, and they needed a grommet, and they needed they were facing a massive shutdown because all of these grommets that are used for their electrical cables, the manufacturer had essentially gone bankrupt, and they were looking for alternate sources. It's a great 3D printing story and use case. So we were able to turn around and get the part printed and do their initial supply within 10 days, and then maintain the supply throughout the year. If they had needed to retool, that would have taken a lot more time to get them running. So this is an example of those grommets. We were able to, the other good part about this story from a 3D printing use case perspective is that we were able to actually, do the side-by-side comparison on these injection molded parts. And in this particular case, especially with thermoset materials, injection molded thermosets actually have much longer cycle times. And we were able to prove that 3D printing could actually have the same level, the same cost structure as an injection molded part, and have similar production times. So very exciting outcome from that. Another use case, we worked with Deutsche Bahn for looking at our printed systems for brake membranes. So this is a case where you can, where it's able to hold air pressure. And in the brake systems, it had to be able to hold air pressure and go through a switching process. So this is, it's not actually used to brake the train, but it's used to manage the pneumatic switches. And here we were able to show that our materials outperform the incumbent material in terms of exposure to heat transfer oil, ASTM oil, gasoline, tensile strength, and really maintain the shore hardness. And this is another example of, let's see if I can get that to move. Playing the video. Anyway, what you would see in this video is really going through a 10,000 cycle test, and able to maintain the durability. Even along similar lines, this is a part that we printed for an axle. This was able to travel on an axle as a boot, for sealing in all of the grease, etc., on the axle. Was able to go 100,000 kilometers in terms of number of rotations. So again, just proving that we have the same durability and strength as the conventional. So we have a range of resins that we print with. Some that have better compression sets, some that have better tensile properties, usually in a range of hardnesses. We're really excited about our Chromolast resins that have very low compression set. And this is really important for a lot of seals and gaskets where they need to be sealed under pressure and then be able to maintain their strength and rebound. And here we were able to show compression set that is about 10 times better than the next elastomer in 3D printed grades, and essentially right in line with what industrial elastomers for these kinds of applications require. And then another component of our technology is this pathing software for quality printing. We really need to, if you take 3D printing off, if you take slicing software, pathing software off the shelf for standard FDM, the main difference, there are two main differences. One is that FDM slicing and pathing is not designed to fill a part 100%. It'll come close, but it doesn't fill a part 100%. And then the other element is that with our printing, we're controlling a pump. And so there's a lot more flow control that we can bring to bear there. And so, and really what we've been able to develop is a suite of software that facilitates G-code development for a range of parts, and bring that extrusion control and path control so you can get 100% fill. I see a couple questions. I'll hit them very soon here. So overall, I think what we've built here in Minneapolis is the key ingredients for manufacturing. So we have high strength materials and parts. So this is really helping us bring that value proposition of 3D printing and additive manufacturing that we're all about, bring that into manufacturing environments. Our printer is very low cost and fast. And that allows us to have a cost structure that can be very competitive with other manufacturing means, but also bring that versatility of manufacturing to the manufacturing floor. Our materials are very adaptable, and really holding that all together is software. that we've developed that really makes it possible to print with these materials. So that concludes my talk, and I'll answer any questions you have. I see one question about range of dimensions, how big and how small. Um, I, in terms of size of part, we prefer to have parts that are about, let's say, 2 inches in diameter and bigger. We've been able to print parts as small as, a centimeter in diameter, and about an inch tall. But we really, the technology is really well suited for large parts. The largest part we've ever printed is about 4 feet tall, and then we've also printed parts that are even 5 feet long. So we're able to go quite large and bring that value proposition of a good solid part to the table there. In terms of feature size, um, and this is in terms of surface quality, we're able to get a very smooth surface finish. So we're able to achieve surface finishes that have extremely um, low roughness, but a feature size, which is distinct from that smooth finish. The feature size, we are limited to about 1 or 2 millimeters, but the smoothness is well below 50 microns. Um, and we're able to be, in terms of resolution and placement of our and accuracy, is about 0.2 millimeters. So hopefully that answers your question. Definitely much better suited for large parts. Um, but the smoothness actually brings a lot of the features of a high resolution print. Um, then there's a question of, do we sell materials or systems, or is our business model to be a part supplier? Our main business model is to sell materials and systems. Um, but we do sell parts if that's the business model that our customers require. So usually we'll sell, we'll start by selling parts with a given customer until they're comfortable with bringing the printing in. But there are some customers where printing is or manufacturing is not really core to their business, and in that case, we'll supply the parts. So hopefully that answers that question. Any other questions I can answer? Oh, I have an example just to if we have a little bit of time. So this is another example of a part and this is where the large parts are helpful. So the important thing about this part is that and there's a lot of features to it you probably can't see in the video. Um, but this part is one where if you tried to mold it, you'd have to cut into a very large aluminum mold. And for us, when we print it, it's easy for us to print on the print platform, really this kind of size and dimension. So it's another example where we're seeing a lot of value propositions against the conventional manufacturer, because you're replacing a lot of expensive processes with additive. So.
All right. Thank you, Cora.
You're welcome.